Welcome everyone to our first lesson in Unit 2. Our lesson today is going to be on properties and changes of matter. We're going to take a look at both chemical and physical properties of different types of matter as well as chemical and physical changes. So today you're going to be able to distinguish between those two different types, chemical and physical changes. We're going to use particle diagrams, where you will use a particle diagram to differentiate between elements, compounds, mixtures, and different phases of matter, solids, liquids, and gases. And we'll also take a look at a few different types of mixture separation techniques like filtration, distillation, and chromatography. And you'll be able to describe the processes of those three types. So to start off, chemistry, really this is our first unit getting into some good chemistry content. So to start off, chemistry is the study of matter and the changes that matter undergoes. And anytime there is any change with matter, there is an associated energy change. So chemistry studies those energy changes in different types of matter. And matter, if you remember this from either 8th grade science or throughout your travels as a student, throughout the years or probably back to middle school, you know that matter is anything that exists that has a specific mass and occupies a specific volume. That makes up pretty much every material thing that we can think of. Now we'll take a look at a couple different types of matter. Now we can classify matter in two major categories: substances and mixtures. And we're going to take a look at substances first. Substances are considered homogeneous, meaning that they are the same or have a uniform composition, and they are considered pure. There's two different types that we'll take a look at. First one are elements and compounds. They're all composed of the same thing. That's why we call them pure. Now in the picture here we have examples of both elements and compounds. And elements are anything that we can find on the periodic table. And those are the only two elements that we have in the picture here, copper and sulfur. We can find their symbols and other information on the periodic table of the elements. The other four substances here are compounds, meaning that they have a set ratio of elements in their formula that make up their composition. For example, sodium chloride down here has a set ratio of 1 sodium atom to 1 chlorine atom. That makes up the formula for that compound. And as long as we only have sodium chloride inside this beaker here, it is a pure substance. It's only sodium and chlorine, but because they're combined chemically, they are a compound and they are in a set ratio. So that substance by itself would be considered pure, even though it contains two different elements. So the two types, again, are elements, and these are substances that cannot be decomposed by chemical change. And this is important. We can't break down an element beyond its singular atom without changing what the substance actually is. So we'd say to a certain extent that that's the lowest divisible particle that we can have and still retain the same properties of that element. And these elements are made up of atoms. Decompose means to be broken down into smaller parts. And we can't do that with elements. We can break them down into smaller parts as far as subatomic particles, but then it's no longer going to be the element. Elements are listed, as I said, on the periodic table. They always start with a capital letter. They don't have to have a lowercase letter, but if they do, it would come second. So the first letter always has to be a capital letter. Compounds are going to have two or more elements that are chemically bonded to each other. And as I said, they're going to be in a set ratio. But compounds can be decomposed by chemical means back into their separate elements. We could take that sodium and that chlorine atom that are combined in sodium chloride, and we can, with certain techniques, separate them so we're left with sodium and chlorine, which would be by themselves two pure elements. And we'll do a little practice here. Some things that you might see on your Regents exam. These are two pretty common questions, and they're going to test two different things. The first one says, which substance cannot be broken down by a chemical change? When we see that a substance cannot be broken down, then we know that elements cannot be broken down any further by a chemical change. So in this case, what we're looking for is an element. Now, some of these compounds on here, this is generally how this question works. You'll be given one element and three compounds. And some of these might not be as familiar, but they will become familiar. Water, you're probably familiar with. That is a compound. It has a formula of H2O. Ammonia is also a compound. It has a formula of NH3, and we can find these in our reference table. And ethanol is an organic compound that contains carbon, hydrogen, and oxygen. So each of these three examples can be broken down into separate elements. We could separate the hydrogen from the oxygen from the carbon, or the hydrogen from the nitrogen. It would no longer be ammonia, but it would be its individual elements. So in this case, the substance that cannot be broken down is tungsten. It's the only element on there, and we don't break down elements beyond their single atoms, at least with chemical change. Now, the other side of this question, you might see it in this form as well. Which substance can be decomposed? So if something can be decomposed by chemical means, this means that it has to be a compound. And generally, with this question, you're given three elements and one compound, and you're left to determine which one is the compound. Now, for each of these, we can find these on the periodic table. They do have a symbol. They're also on table S, so we can look up their name. Methane is the only one that has a set formula, a ratio of elements in the compound, carbon, 1 carbon to 4 hydrogen. So that compound can be decomposed by chemical means. Now, when we take a look at chemical reaction or chemical change, these are reactions in which something new is going to be created. So what we start with isn't necessarily there after the reaction. It could completely disappear. We might have part of it disappear, it might turn into something else, but we're going to come up with some type of new product after a chemical change. Some examples of this are rusting, burning, reacting, exploding, and fruit ripening. So if you have a campfire in the summertime and you throw some logs on the fire and you let it burn for a couple hours, you come back, the wood's not there anymore. It's been changed into something new. The wood that was there through chemical change becomes ash, heat, light, water vapor, carbon dioxide, and probably a whole slew of other different things that are in the smoke. Fruit ripening. If you start with a green banana, you're no longer left with the green banana. Once it ripens, it becomes a yellow banana. The starches on the inside of the fruit begin to change into simple sugars and become sweeter. So what we start with is not there at the end. Something new is being created. Now, the other side of our matter classification chart here are mixtures. And we're going to look at two different types today. We'll talk about a couple different examples. So mixtures are combinations of substances. Now, everything is made up of a substance, element or compound, but we can take elements and compounds and combine them together and create mixtures. But mixtures are not chemically combined together. they can still be broken apart by physical change. So we can take advantage of a mixture's physical properties to separate components in a mixture. Just depends on the type of mixture we have and what techniques we'll use. So homogeneous mixtures are called solutions. And you're going to see this designation a lot, this AQ. And what it means is it's an aqueous solution, meaning that something is going to be dissolved in water. So if we see, we'll go back to that sodium chloride formula. If we were to see sodium chloride with an AQ designation coming after it, that means we had sodium chloride that's been dissolved in water. And that's really the biggest one that you're going to have to be aware of and what it means. These other three here we'll talk about, but there's no designation that we'll use. You kind of just have to be aware of what they are. Tinctures are solutions, again homogeneous because it's a solution, where something is going to be dissolved in alcohol. An amalgam, these used to be, I don't think they're really used too much anymore, as fillings in your teeth. So mercury is going to be used to dissolve a different metal, and then we get an amalgam, and that was used to put into cavities in your teeth as a filling. It'll solidify, and they seal and work very well as fillings in your teeth. But the mercury in this case is used as the solvent, the component of a solution that does the dissolving. Now the last one is alloys. And alloys are mixtures or solutions of different metals. And those metals, when they become alloys, they're never solids that are pounded together, but they are liquefied and combined, and they do become homogeneous when they're liquefied and become a solution, and then we're left with this new type of metal, and we'll have different types of properties than what we started with, and that's true for all of our mixtures. So in a homogeneous mixture, all of the materials are equally dispersed. We could zoom in on all the components of that mixture, and everything's going to be evenly spaced out. When compared to a heterogeneous mixture, these have varying compositions throughout the sample. For example, muddy water. The composition at the bottom, we're going to have materials that are heavy and more dense that sink to the bottom, like mud. And then we're going to have things like water that are going to be more towards the top, maybe some pieces of wood that might be floating. But we're never going to have all those particles evenly dispersed throughout the solution to make it homogeneous. Italian salad dressing will separate when it's put in the refrigerator, and we're going to get the oil on the top, and we'll get the vinegar on the bottom, and any other pieces that happen to be in the salad dressing, all the good stuff, most likely more dense, and will sink to the bottom in the water layer. Soil, if you put your hands in soil and pull something out, you're going to get something different every single time. If you think about it, if soil was homogeneous, we'd have to have equal parts of worms in every single part of soil everywhere. And that's not the case. You might get a worm sometimes, you might not. You might get some sticks, you might get some rocks, you might get clay, you might get sand. It's varying composition, and it's not the same throughout. Cat vomit. My cats tend to vomit up their food in a nice long tube, and it never looks the same. Sometimes there's hair in part of it, sometimes there's not. Sometimes it's liquefied, sometimes it's solid. So that is not a uniform mixture, so that is heterogeneous. Now this next slide, we're going to talk about a couple techniques. These are not in your notes, so make sure you add these in there somewhere. And these are the three techniques that are generally tested on your Regents exam. And each of these techniques uses physical properties of the mixture in order to separate components. Filtration separates components of a mixture based on particle size. So we could use a filter, let's say in coffee. We pass water and coffee grounds through a filter. The coffee grounds are much bigger than the water molecules, so the water molecules can pass through the filter, and the coffee grounds are left on top. And we can change the filter size to collect different size particles. Just depends on what the application might be. Now, distillation is going to separate components of a mixture based on boiling point. And in distillation, I'm going to talk about crude oil distillation. Crude oil we put into a big, huge vat, and we heat it. And it goes into what we call, as it starts to boil, it goes into a distillation column. And as the boiling point of different substances are reached, as the temperature rises, they start to boil off, they go up this column, and they're collected in different tubes. And depending on the boiling point of the substance, they're going to rise and collect and condense at a different point in the tube. The hot gas will rise up through here, and depending how far it traveled, it's going to lose energy, it's going to cool down, and it's going to be collected after it condenses into liquid into one of these containers. And we're going to get things like oil, gasoline. Down here, we're going to get things that you would use on your driveway like tar. That's kind of all the leftover garbage at the end. We might get things, kerosene, propane. We're going to get all these different substances from our crude oil using distillation. And again, that will use the physical property of boiling point to separate those components. Now, chromatography, and we will do a lab on chromatography, is going to separate components of a mixture based off of their polarity and their attraction between what we would call the mobile phase, which is a solution, and the stationary phase. We'd put our mixture on this stationary phase here, and the mobile phase is going to try and carry, as it wicks its way through this stationary phase, it's going to carry the components of this mixture that we put in here along the stationary phase. And depending how attracted it is based off of polarity, which is basically saying like the molecule has a positive or negative charged end as opposed to not having one, depending how attracted it is to the stationary phase, it's going to move farther along the stationary phase. And depending on that attraction, different components will separate along the stationary phase depending on their attraction in the mobile phase. So components of a mixture can be separated using chromatography, and that's based off of the physical property of polarity. For example, water is a polar molecule because water has a partial positive end and a partial negative end, kind of like a battery. Particle diagrams. You guys will have to use particle diagrams to differentiate between different types of matter. And particle diagrams can represent atoms of each element with using different types of dots. And the arrangement of the dots will tell us about the type of matter that it is and the composition of the matter. And we can use pretty much any key that we want, but we'll try and keep it simple. We're going to use a little open circle here to represent a single atom of an element. So in the box here, we would have 5 atoms. And depending on their spacing between each other, we can determine what phase of matter the element is in. And that's going to depend on how close the proximity atoms are to each other and what type of energy they have. Now, a diatomic molecule, di meaning two atoms, diatomic molecules are still elements. They're still the same type of atom. For example, chlorine. We never find chlorine atoms by themselves as a single element. Chlorine is part of a group of elements, which you're going to have to remember this, which we call Brinkelhoff. Each of those elements exists as a diatomic element when they're by themselves. And chlorine is in there, as well as bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And again, you're going to have to remember this. So these are diatomic molecules, and we always write them diatomically as Cl2, not just Cl. And in our diagram, we see that there's two atoms bonded together, two chlorines in this example. Now this one here is a compound, and we can have a couple different types of compounds. And again, we won't get into the specifics of the two different types of lead oxide here, PbO and PbO2. We'll get into that later in the year. But what we need to know is that if we represent a lead atom with a darkened larger circle and an oxygen atom with a smaller open circle, we can determine what the formula is based off of what we see in the particle diagram. So in this case, we have one lead and one oxygen, so the formula is PbO. Over here, we have, again, still one lead, but now we have two oxygens attached to each lead. And each of these are the same. So in that instance, this is a pure substance. It's all PbO2. There's nothing else inside that container. On the left side, it's all PbO, lead oxide. Now, when we get into mixtures, we're not just going to have one type of matter. In each of these cases here, inside the box, there's only one type of matter. We don't see anything else there. If we open this barrier here, sure, they could mix together, and then we'd have a mixture. But with the barrier up, they're separate and they're pure substances. Now we can have mixtures. And depending on what different types we have, we can determine what type of mixture it is. So on the left example here, there's two different types of circles. This big solid one and the small open one. Since there's nothing else combined with it, we can assume that those are two atoms of an element. And it's homogeneous because they are evenly spaced throughout the container. On the right side, we have again, homogeneous mixture because everything is evenly spaced in there. But now we have an element and a compound. We have a solid large circle, and then that solid large circle with two smaller ones. So we can tell based off of what's in the box, is it a compound? Is it an element? Is it a mixture? What phase could it be in? Now, to show you an example of a heterogeneous mixture, now we have two elements in the one on the left here. We have an open circle and a closed circle, but all of the closed circles are on the bottom left, and all of the open circles are more towards the upper right 2/3 of the box. So this shows a heterogeneous distribution because things are not evenly mixed. Same thing with the one on the right. They're not evenly mixed because we can pretty much draw a line through here and separate everything, one on the bottom, one on the top. We know that this is an element because it's one single atom. And this is a compound because we have two or more atoms combined in a set ratio. In this case, it looks like it's 1:1. I'm going to go back to, we'll look at it this one. These elements and compounds, depending how close they are together, we can determine their phases of matter. And the closer things get together, we're going to have solids. And the farther they are apart, we're going to have gases. And in between, we'll have liquids. And we'll get into that specifically in our next lesson. So physical changes are only changes that change the appearance of a substance, not actually its chemical identity. So when I snap my pencil in half because I'm frustrated, it's still a pencil. It's not changing what the pencil is, just in some smaller pieces. Now, physical properties are properties that we can observe through physical change. Like our melting point, our boiling point, malleability or the ability of a metal to be hammered into thin sheets. Some examples where we're using physical properties are separating, filtering, melting, boiling, dissolving. If you dissolve sugar into water, you can separate the two by letting the water evaporate, and it'll leave all the sugar left behind. If you take a sample of seawater and you bring it home and you leave it out, all the water is eventually going to evaporate and you'll be left with all of the minerals and salts that were in the seawater. Evaporating, crushing, stretching are all physical properties. Chemical changes are changes that result in actually changing the composition, the chemical composition, the chemical identity of the substance. And pretty much anything can be reversed. Any chemical change can be reversed as long as we have enough energy, but we have to use another chemical change to change it back. The chemical properties can only be observed through chemical change. For example, the chemical property of reactivity. We will see corrosion of metals, flammability. Once metals corrode, the copper that once was the Statue of Liberty is no longer there. It's become some type of copper oxide mixed with other minerals that are now made it green. So that's not pure copper anymore. It's changed its chemical identity. Stability, well, that has to do with chemical decomposition. For example, hydrogen peroxide, H2O2, looks very similar to water, but we have one additional oxygen. And this is a very, very strong oxidizer, especially in a pure form. You find this at the store in a solution that I believe is less than 3%. And I'll do a couple different demonstrations where I use 30%. But if you get 30% on your hands or on your skin, it will break it down pretty quickly, and it turns it a pretty nice white, bright color. Not that you want to see your skin that color, but it is put into a brown bottle because it will react with the light, and it breaks down just by itself. Now, the heat of reaction, this has to do with how much heat is being brought into a reaction or out of a reaction. Okay? And burning, we were talking about with the campfire, releases a lot of heat. Combustion in an engine releases a lot of heat. And depending on how much material we have, how much fuel we have, we can determine how much energy is available to give off using our heat of reaction. I got a short little video for you guys on how we can use some different techniques when using substances and mixtures.
We are surrounded by countless substances. Some are pure, but the large majority are formed by mixtures of two or more pure substances. Pure substances have a homogeneous appearance. Each pure substance is characterized by having specific properties that distinguish them from all other substances. In contrast, mixtures do not have specific properties. Their properties depend on the substances or components that form them. The components in a mixture can be extracted using appropriate separation methods. Depending on their appearance, mixtures can be heterogeneous or homogeneous. The components in a heterogeneous mixture can be distinguished with the naked eye and are not evenly distributed. The components in some of these heterogeneous mixtures can only be distinguished using a light microscope. This is the case of colloids. The components in a homogeneous mixture or solution are evenly distributed, so they cannot be distinguished, not even under a light microscope.
And that's what I have for you guys for today. If you have any questions, make sure you write them down. Make sure you get your questions answered. And I've always kind of wondered, what do I do if no one laughs at my chemistry jokes? And I figured I'm just going to keep telling them until I get some reaction. Hope you guys have a great day.